Hello, so today we are going to discuss the Brachistochrone problem. Before we go into more details about the problem, let's see what the statement of the problem is. So, find the curve along with which a particle will slide in the shortest time under the influence of gravity from a point to a lower point not directly beneath. So what we are basically asked is that let's say there are 2 points A and B at a certain height, and A is not directly above B or directly below B, it's somewhere at a distance as shown in the diagram, and we have to find a path along with which the time taken for a certain particle to reach B is the shortest, or like it takes the least time. Now a general intuition would be that, hey, let's just draw a straight line. Unfortunately, that's not the case. Let's see why. Now, if I had to move from point A to point B, and we need to remember that gravity is acting here. So as I move from point A to B, I actually want that the slope is greater in the beginning so that my particle gains a velocity and moves towards B. So as soon as it reaches the point in the middle, it would have gained a certain velocity and would continue to move back with that velocity when it reaches B. Now there's a special name for this particular curve or path that the particle will take. Any guesses? Well, it's called a cycloid. And as you can see, the red curve over here, that's a cycloid. You see how the curve is more here? Now you could imagine that why not anything else? You would see that if I were to take a path, let's say like this, a straight line and then complete drop, the gravity wouldn't act on the particle and that wouldn't quite work. Now let's answer what exactly a cycloid is. So here as you see in the diagram. Now if I were to take a point on a particular wheel or a circle, let's say take any point, let's say this point, and as the circle rotates and translates, so it's basically moving along its axis and also moving forward. So this particular point would keep moving ahead, and the trajectory of that particular point would be something similar to the pink curve that you see. And this pink curve is our cycloid. Now, before we dive more into the solution of an initial problem, let's see what the equation of a cycloid is, because after all, it's the final answer. Now, you see the diagram over here. I have a point P on a certain circle, which is going to move and form our cycloid. I have distance PQ, and then this is the center of the circle. This is another point T, and O, the origin. So, if you were to notice, we have the x component of the point P and the y component of the point P. And if I were to find the x, this distance, it would be OT, this distance minus PQ. Now, OT is going to be r theta, if you recall, and PQ is going to be the sine component of this particular distance r. So we can say that x is OT minus PQ, which is r theta minus r sine theta, which is r into theta minus sine theta, which is the x component of our point P. Similarly, for y, I need this distance over here, which is going to be OT. No, this is going to be TC minus QC. Okay, cool. Which is QC is the cost component of R, and CT is my radius itself, which gives me R into 1 minus cos theta. And here we get the equation of our cycloid, of the components, obviously. Since we are done with the derivation of the components of the cycloid or the coordinates, let's get back to our initial problem. Let's try to prove that a cycloid itself is a solution to the Brachistochrone problem. Now, see, we have the time. So you recall that our whole aim was to find the shortest time that a certain particle will take in moving from point A to B under the influence of gravity. So I can say that the time t is the distance, the displacement over the velocity, particular velocity that's going to gain when it moves from point A to the point B. Okay, cool. Now, you know that if I were to take a point here, it would have potential energy, and as it descends down, it's going to turn into the kinetic energy. So I can conserve the energy over here. Well, let's do that. You have half mv squared is equal to mgp, and we know that v is basically equal to root 2g by, because v squared minus u squared is equal to 2g pi, and u squared over here is going to be 0, so this gives us v is equal to root 3g pi. Now the distance ds, the overall displacement, is going to be the displacement in y direction plus the displacement in x direction. So that's basically going to be its magnitude, which is the x squared, distance traveled from this direction, and plus the square of this, the distance traveled in this direction, rooted. And as you take the x to the bottom and solve it further, you see that you get an equation like this. So you got the ds, and now I'm going to substitute back the ds into this equation, and I get something like this. I have t is equal to root 1 plus y dash squared by root 2gy integrated from a to b. Now, any guesses how you're going to solve this equation, this integral? Well, our simple solution is the famous Euler-Lagrange differential equation. But if you were to notice that this particular equation of mine, there's no x component, meaning I can use a very special case and use the Beltrami equation, which is basically f minus y dash del f by del y dash equal to a constant. Let's apply the equation and see how it turns out. Now, you have the Beltrami equation and the f minus this particular stuff. Now, as we solve the equation, we get y dash being equal to dy by dx, which is a minus pi by under root. So now, in order to solve this integral of dx, we know that we are going to have to take an integral from 0 to y along the y direction from root over y minus a minus y into dy. So if we were to make a trigonometric substitution at y equal to a sine squared theta, we would actually get that, oh hey, the solution, oh, it actually is a cycloid, as we saw. It's equal to a constant to y minus cos phi, and v is equal to x is equal to b into phi minus sine phi. There is another question must pop in your mind that, okay, you did prove that it's a cycloid and all that, but you never really proved that it's actually going to take the shortest time. I guess it is out of the scope of this video, and you need to apply variable calculus in order to actually find out the time that it's going to take from point A to point B. Maybe that's a thing for another day. And if you found this problem interesting, maybe you should check out another problem, the Tautochrone problem, which is very similar to this problem. And yeah, thank you.